I want to talk about this molecule here where carbon is bonded to bromine, fluorine, chlorine, and hydrogen. And I could have used any example as long as the carbon were bonded to 4 different groups, and we'll see why that is in a few minutes. And what I want to do is I want to focus on looking at the structure of this molecule in 3 dimensions, because as it turns out, there are 2 different ways we can draw the molecule in 3 dimensions. In one of these drawings, you can see I have the fluorine going to the right and the chlorine going to the left. In the other one, I have the fluorine going to the left and the chlorine going to the right. And that might not seem like such a big deal, but it really is. And we'll be able to see that if we look at this molecule using a different model set. And this particular model set much better at representing 3-dimensional structures. I can move the individual molecules, I can rotate them if I want to, and what I want to show you is that these are actually 2 different molecules. And the way that I'm going to do that is by trying to take one and superimposing it on the other. So I'm going to drag it over, and then I'll do some rotation on it. And the rotation mode is a little bit clunky, so it's a little bit hard to get it perfect. But what I want you to see is that I can line up 2 of the 4. So I can line up the blue and the purple here. Twist this a little bit more. So the blue is lined up with the blue, purple lined up with the purple, but the red is lined up with the white and the white is lined up with the red. And no matter what I do, no matter how I twist or turn these, I'll never get them to line up perfectly. There's another feature that I want you to notice about these molecules also. And in order to do that, I'm going to return this one to its original orientation. And what I want you to notice about these molecules are that they are mirror images of one another. There's a mirror plane that goes right down the middle here, and the red is a reflection of the red, the purple is a reflection of the purple, blue going away in this direction, blue going away in this direction, and so forth. They're mirror images of one another. So if we look at the 2 things we've said about these 2 molecules so far, we said they're not identical. In other words, they're non-superimposable. I can't take this one and twist it and turn it in a way so that it matches up perfectly with the other one. And also, we said they're mirror images of one another. This is a reflection of this, and so on. We have a name for a pair of molecules that meet both of these criteria, that are not superimposable and are mirror images of one another. We call these molecules enantiomers. Now, it's going to be important for us to identify enantiomers, and we'll talk in class and in other places about why enantiomers are important to be able to identify. But we want to be able to look at a molecule like this one right here and say, yes, this is going to have an enantiomer, or this is not going to have or not going to exist as a pair of enantiomers. And in order to understand how we do that, I want to look at another set of molecules. I'm going to make just a small change to my original molecule. And what I've done in this new molecule that I've made is I've replaced the fluorine with a hydrogen. And I've redrawn both of these possible representations here as well, where the fluorine has been replaced by hydrogen. And making this small change has a very big impact on the actual 3-dimensional structure of the molecule. And in order to understand that, I want to look at these molecules again in my alternative model set. And I've drawn these here, and you can see the red fluorine in both of them has been replaced by the white, which I'm using to represent the hydrogen in these molecules. And what I want to do is what I did before is try to take one of these and bring it over and try to superimpose it on the other one. And what I hope you can see is, although I didn't rotate it perfectly, all 4 groups are lined up. The blue and the blue are lined up, the purple and the purple are lined up, white and white and white and white. So these molecules are identical to one another. They're superimposable. I can take one and drop it on top of the other. Now I want to point out these molecules still are mirror images of one another, or these two drawings are still mirror images of one another. And in order to demonstrate that, I'll rotate this one back to its original position. So there's a mirror plane right down the middle here. This is a reflection of this. The blue is a reflection of the blue, and so on. But the two are identical to one another. Why are they identical to one another in this case, but in not this case? Well, if I do a little bit of rotation of one of them, I think we'll be able to see it. And I'm going to try to rotate this one just like this so that the blue is coming out towards us. And what I want you to notice is that there is a mirror plane going right down the middle here. If I made and what we call this mirror plane going through the molecule is a plane of symmetry. So there's a plane of symmetry right through the middle of this molecule, where the left half of the molecule is a mirror image of the right half of the molecule. We have a plane of symmetry here. If I try to do the same thing on the first set of models, and I will rotate this one again with the blue coming straight out at me. Let's see if I can get that done. Turn it a little bit more like this, and then like this. What you should notice in this case is that the right half and the left half are not mirror images of one another. In other words, this molecule has no mirror plane going through the middle of the molecule. Or in the way that we've been saying it, there is no plane of symmetry in this molecule. So if we summarize the things we've said about this second set of molecules, the two structures are identical. They're different drawings of the same molecule. And the reason for that is that there's a plane of symmetry in this molecule. We saw it right here. You can also see it in this set of drawings. This molecule does not exist as a pair of enantiomers. So what I want to do now is summarize kind of what we've talked about with regard to enantiomer. So the first thing we've said are that enantiomers are non-superimposable mirror images. The next thing we said is that the enantiomers have no plane of symmetry, and sometimes we call this being asymmetric. And finally, often the asymmetry that we find that gives us enantiomers is found on a carbon bonded to 4 different groups. And you'll notice that's the difference between our first molecule and our second molecule. This carbon is bonded to 4 different things: bromine, chlorine, fluorine, hydrogen. This carbon is not bonded to 4 different things. It's bonded to a bromine and a chlorine, but 2 of the things are the same: hydrogen and hydrogen, 2 identical groups. And that's why this molecule has a plane of symmetry and this one doesn't. And as I said, that frequently is how we can identify these asymmetric carbons, these molecules that are going to have enantiomers or exist as a pair of enantiomers. We have 4 different types of groups on the central atom.